Hello, everyone, and thank you for joining us on a bonus webinar for our AIA California Climate Action webinar series. My name is Stephen Hall. I'm California's Vice President of Professional Practice. As you know, AIA California is currently hosting a monthly Climate Action webinar series. All previous meetings and recordings and bonus sections like this one and the information on future webinars are available on the Climate Action portion of the AIA California website. In partnership with the National Ready Mix Concrete Association, we're happy to have Lionel LeMay and Don Thompson join us today. Concrete is the material of choice for the tallest buildings in the world and the infrastructure designed to last centuries. To meet demands of these cutting-edge projects, concrete must be stronger, more durable, and more workable than ever before. This presentation explores how new products, manufacturing methods, and research are developing innovative concretes to meet these new challenges. Bendable concrete, smog-eating concrete, carbon capture are just a few examples of the new technologies enhancing a product that is more than 5,000 years in development. On a personal note, I really love concrete. In the early 70s, I worked for Paulo Solari in the Arizona desert building Arnold Fulsani. The unique uses of concrete that we built, like the half-dome ass that we hand-placed low-slump concrete on top of carved and colored silt mounds, led me to appreciate all the possible design features that can be done with concrete. As a reminder, using the question and answer box at the bottom of or top of your screen, feel free to type in questions for Lionel and Don to answer during the Q&A portion at the end of the webinar. Frank Matchi will be helping us on that. So moving on, Lionel LeMay is Executive Vice President, Structures and Sustainability for the National Ready Mix Concrete Association. I won't give you the acronym. He leads a team of professionals that offer building owners and designers the cost-effective, durable, and sustainable concrete solutions through communications, education, research, design assistance, and codes and standards advocacy. He has written over 100 articles on concrete design and construction and is co-author of several books, including the McGraw-Hill book, Insulating Concrete Forms for Residential Design and Construction, and contributor for FEMA 320, Taking Shelter from the Storm, Building a Safe Room for Your Home or Small Businesses, along with several ASCE publications. Mr. LeMay is a registered professional engineer and structural engineer in the state of Illinois. He's also a LEEDS accredited professional and serves on committees of the American Concrete Institute and the American Society of Civil Engineers. Mr. LeMay holds a bachelor's and master's degree in civil engineering and applied mechanics from McGill University in Montreal, Canada. Don Thompson is a Senior Director Building Innovation, or is the Senior Director Building Innovations for the National Ready Mix Association. Based in Kennesaw, Wisconsin, he supports the Build and with Strength program, demonstrating the first cost and long-term advantages of ready-mix concrete building systems throughout 8 Midwest states. A licensed architect and LEED accredited, Don has over 20 years of practical experience in design and construction. More recently has worked for over 22 years in the cement and concrete industry, holding various technical, promotion, and sales positions. Don holds a BA and Master's in Architecture from the University of Illinois, Chicago. So on that note, I'm going to sign off or turn my video off. You don't need to watch me, and turn it over to Lionel and Don. Thanks.
Thank you, Stephen. Assuming you can see my screen.
Yes, I can see it, so hopefully everybody else can.
Yes,
All
we're good.
Thank you. Well, welcome everybody, and thank you for the opportunity to present to you today of the AIA accredited course, Concrete Innovations. Both myself, Lionel LeMay, and Don Thompson will be presenting today, and the sponsors for this, along with AIA, of course, is our Build with Strength program, along with National Ready Mix Concrete Association and the California Nevada Cement Association. Bear with me, my slides don't seem to be advancing. There we go. So you already saw the learning objectives for the course. It is AIA accredited, and of course AIA will be recording your attendance and participation in the class. So let's get right into it. Defining the problem. So the problem is, of course, climate change. We're seeing more intense storms, weather events, California, of course, wildfires and droughts. Not all that many, windstorm events, but of course the rest of the country, and currently, as we speak, experiencing hurricane as we're presenting today, and tornadoes. So those flooding. So those events, and California experiences flooding as well, and those events are generally caused by climate change. Of course, the building industry is partly to blame for increasing climate change through CO2 emissions into the atmosphere. We build a lot, and we're responsible as the design community for designing those buildings and hopefully reducing carbon footprint through two means. One, designing buildings that are low energy, that reduce carbon footprint during the use phase of building operations, which is pretty significant. In fact, the most significant component of CO2 emissions. And then also, though, selecting and using materials in a way that reduces the embodied carbon emissions. That's the emissions from the manufacture and construction of buildings. Every year, we build about over 6 billion square meters of buildings throughout the world. That's nearly 4,000 million metric tons of CO2 per year. And by 2050, it's predicted by Architecture 2030 and other sources that the operational carbon emissions from buildings and embodied carbon emissions from buildings will be about equal, which means each of those needs to be addressed in a significant way. The challenge is that building materials do emit significant carbon emissions. So embodied carbon from building materials produce about 11% of the annual global greenhouse gases. And concrete and iron and steel produce about 9% of those annual emissions. Now, likely the need for these robust materials will be in demand for the next foreseeable future. And the trick here is to understand how can we minimize environmental impacts of these building materials. And specifically today, we're going to talk about concrete. What are the solutions? Well, it really is concrete innovations. And basically, we're talking about 6 basic steps: more efficient concrete mixtures, admixtures, blended cements, supplementary cementitious materials, carbon capture technologies, and high performance concretes. So what do these two buildings have in common? Well, they're both places of worship. Both are built in Rome, Italy. But most importantly, both are built with concrete. And at the time, they were both innovative in the use of concrete. So the Pantheon, built in Rome in 27 BC, used Roman concrete, was unique at the time, using volcanic ash and aggregate that was mainly recycled, some rock, but crushed tile and brick. And the Jubilee Church, which of course everybody knows the Pantheon is still standing today, 2,000 years later. The Jubilee Church was built in Rome in 2003. And the innovation there is that they used photocatalytic concrete, which is self-cleaning. And we'll get into more of that innovation later on in the presentation. Now, modern concrete is not that old. Really, ready-mix concrete is just over 100 years old. And, delivering it in trucks is even less started only about 80 years ago. But Portland cement was invented in 1824, and it's combined with quarried aggregate and water really to make concrete. Those are the three main ingredients. Without that, you can't really make concrete. And let's face it, concrete is not always synonymous with innovation. It's been around for a long time. But in fact, most concrete today uses some form of innovation, which we'll be talking about today. The first innovation, and really the most important, is that we need to use the most efficient concrete mixtures. And Portland cement, which is the most important ingredient in concrete, is the glue that holds it together. It's one of the most valuable materials on the planet. It's cost effective, it's available everywhere, it's durable, strong, tallest buildings, largest buildings, longest runways, highways, everything is built with concrete. And it's hard to imagine a building today built that's not built with some component that is built with concrete. And so that Portland cement needs to be thought of as this valuable material that can't be wasted. And even if you don't consider the environmental impacts that may be associated with Portland cement, it's the economic impacts that you could consider. So both are important. If you can optimize the use of Portland cement, basically you're reducing the embodied impacts of concrete. We really promote the idea of using performance-based specifications. There's not a lot of time to go through that today, what that really means, but basically it means no limitations on materials and quantities. The standards today for concrete and the building codes really don't provide limits on the use of cement or admixtures or supplementary cementing materials. They are really set by the performance criteria that you set as designers, whether it's strength, durability, stiffness, and so forth. And what's really important is that the producers and the laboratories that are involved in testing concrete are qualified. We can go into a long discussion about why that is, but basically concrete, the design of concrete mixtures is dependent on how well it tests. And if you don't have qualified producers and qualified laboratories who know how to sample and test concrete appropriately, then generally the test results are lower. And that means that the concrete producers have to actually design concrete with higher strength to meet the minimum strength requirements in your specifications. What does that mean? Higher cement contents. And I just talked about how the objective really here is to design concretes with really efficient amounts of Portland cement. We do have a class specifically on this, and if you go to buildwithstrength.com/education, we have links at the end of this presentation as well. We have a whole course on specifying sustainable concrete. I know most people aren't really excited about learning how to specify. We have people specifically for that in most firms, and maybe you would consider having your specifier visit that education program. But we also have a guide spec. You see it pictured on the screen here, and you can download it from our website, and likely we'll provide it to the AIA California so that they can distribute it directly. All right, let's talk about admixtures. These are really important. Almost every concrete made today has some sort of an admixture in it, and most admixtures are there specifically to modify the plastic properties. So they're really contractor-related changes in properties that make concrete placing a lot easier. Let's face it, concrete's not that easy to work with. It has a time limit, it's heavy, it has to be delivered somewhere, it has to be placed on site, and anything we can do to make the placement of concrete easier is important. The first one I'll talk about is water reducing admixtures. They were invented generally to increase slump of concrete, so you could pump it, place it a lot easier, not require as much vibration on site, and so forth, move it around a lot easier. But the main outcome of that is that it actually decreases water demand, which in effect decreases cement demand. Again, going back to this idea that if you can optimize the cement content in concrete and still get the same strength, then that is a positive and it reduces carbon footprint. Viscosity modifying admixtures improves workability. Again, mostly, there's not a huge carbon footprint reduction as a result of that, but anything you can do to make concrete more workable means less water that is needed in concrete, meaning less cement generally. Set accelerating admixtures are important only because high volumes of supplementary cementing materials often causes some set delays for concrete and strength gain delays. And so having these set accelerators can offset some of that delay in using high volumes of supplementary cementing materials. Again, the tip here is really to permit all admixture types. Don't try to limit the use of admixtures because they're so important in efficient concrete construction, and see the guide spec on recommendations there. Now this one is really important. Blended cements are a combination of Portland cement in addition to some other materials. The most common one is called Portland limestone cement, or type 1L, and it permits in the standard ASTM C595 up to 15% interground limestone. Now, interground limestone has nearly zero carbon footprint. It usually is a byproduct of the cement manufacturing process because there's a lot of powder that is generated when crushing limestone as the raw feed for making Portland cement. So if you can take some of that powder, intergrind it with clinker at the end of the processing of making Portland cement, then you can lower the carbon footprint by as much as 10%. And surprisingly, the performance of Portland limestone cement is almost identical to pure Portland cement. So it's really something that you need to specify and create demand for. It's still in this country slow to catch on, but really to me it's a 10% reduction in carbon footprint just by using Portland limestone cement with equal or better performance. In fact, what's great about it is that research shows that you might be able to even use more fly ash and slag in combination with PLC to reduce carbon footprint even further. Now, there are other types of blended cements where you combine Portland cement and slag and Portland cement and fly ash, but for the most part, and they're perfectly fine. They work perfectly fine. But I would say they probably have even further barriers to acceptance, whereas the Portland limestone cement really is, has no effect on performance and still provides that reduction in carbon footprint. So let's talk about SCMs, or supplementary cementing materials. The two main ones that are used, and you probably, many of the projects that you guys work on have concretes made with SCMs. Slag cement and pozzolans like fly ash is being the most common are used in concrete all the time. And honestly, they provide the most reduction in carbon footprint. And I'll tell you why in a second. They're byproducts of other industries and therefore have very little footprint because they don't require a lot of processing. Slag requires a little more processing, mostly in grinding. Grinding doesn't take a lot of energy. And fly ash really is a byproduct of the electric power generation. Yes, less of it is being made, but I'll tell you here in a second why there's still a great opportunity for fly ash in this country. There's some other natural pozzolans, even today, things like meadowkaolin or even volcanic ash can be used. But there's the kind of volumes that are required for concrete manufacturing, really fly ash and slag are the best options here. Just a really quick chemistry lesson. You don't have to memorize this, but it demonstrates why these SCMs work so well. So cement reacts with water to form these cementitious compounds. There are many compounds, but for the most part, the two compounds are CSH, calcium silicate hydrate, and calcium hydroxide. The CSH portion is the portion that are the crystals that really hold the entire matrix together. Whereas the CH really is not very strong. It almost remains in a gel form. We don't see it that way, but it really is not that, in fact, not valuable. You'd rather not have that material. And so when you combine, if you look at the first line that represents the just pure Portland cement with water, when you get the CSH and the CH, but if you combine it with the pozzolan like fly ash, it reacts with the CH to form more CSH. And that's why pozzolans like fly ash are so valuable. It eliminates the material that you don't want in concrete and turns it into the material that you do want in concrete. Now, slag is a little different. It's not really a pozzolan or very little pozzolanic action. It is actually cementitious, but it needs this alkali lime activator, which is produced by the cement hydration process. So it does produce CSH, no CH. So that's a good thing. And then there's a little bit of pozzolanic reaction that does create more CSH. That's why these materials work. It's not just that we're replacing cement. It's actually reacting with the byproducts of cement hydration that make them so valuable. Just a case study. There are many, of course. Most high-rise buildings use high volumes of supplementary cementing materials because they do. One of the biggest benefits of these materials is that they increase strength of concrete. And when you're building a high-rise building, using high volumes of SCMs is just a natural thing to do. Trump Tower, 92 stories in Chicago, huge amounts of concrete, almost 200,000 cubic yards of concrete, which is massive amounts, but all the columns and walls required 12,000 PSI at 90 days. And remember that, because 90 days is important. For elements of a building that don't require to reach full strength at 28 days, by requiring at a later date the strength to be reached, it permits the higher use of supplementary cementing materials. Again, a way to help reduce carbon footprint. The lateral resisting elements, the shear walls and so forth, up to 16,000 PSI. Now, self-consolidating concrete was specified for most of the project because of high reinforcement congestion, and then high volumes of SCMs, one to reduce heat of hydration, and it basically used a lot of ternary blends and in some case quaternary blends. In other words, slag, Portland cement, slag cement, fly ash, and silica fume to meet the requirements. And the whole idea here is, obviously a high-end residential building, 30-foot spans without spandrel beams. And if you've ever seen the location for Trump Tower in Chicago, beautiful vistas of the lake along the Chicago River. Now, this is really, I think, the future of fly ash, because I think I mentioned before, because of our, less reliance on electric power generation through, burning coal, we're not going to have as much high-quality fly ash in the future. But we've been burning coal for a long time to make electricity, and most of that fly ash has been buried in landfills. And so there's a valuable material that is now, by some companies, are actually mining that material, beneficiating it in some way, which means it does need some processing, usually to dewater the ash, but also, in some cases they may be out of spec to be used in concrete. So things like, reducing the amount of unburned carbon, reduce ammonia, and adjust particle size through different processes. So I think this is a huge opportunity for our industry. 1.5 billion tons of coal ash in landfills or more that could, be a source for literally decades. And there are some companies already doing it. Another case study here. This is a project in South Africa, really designed with sustainability in mind. I'm sure many of you are designing projects with similar goals. And in this case, the building came in at 50% more sustainable than the average office building. It reached the 4-star Green Star South Africa rating and used a lot of fly ash in the concrete and reduced the overall concrete footprint by 30%. And the last item I'd like to talk about before handing it off to Dawn to finish off the presentation is really something that is probably not an opportunity today for most concrete, especially ready-mix concrete, is called Geopolymer Concrete. But there's really a lot of promise with this concrete. This uses fly ash and or slag and a chemical activator to form a hardened binder. It's been done. There are some companies that actually have created concrete. It's obviously more expensive than conventional concrete, so it usually is used in very specialized applications, maybe high heat or high resistance to acids and so forth. But creating demand for it will result in more use and the cost of the construction or that material coming down somewhat. The activators include sodium hydroxide or potassium hydroxide. Again, they're highly alkaline, which means they're caustic and hard to handle, expensive to make. That's what makes this concrete more expensive. But the properties are really favorable. So similar strengths, a little bit higher strengths generally than conventional concrete, but lower drying shrinkage, lower heat of hydration, and improved resistance to chemicals. Like I said, the drawback here is that there's a high cost to produce the chemical activator, and handling high alkaline solution, it's just like handling a high acidic solution, very difficult. And you oftentimes need temperature control during the curing process. So ideally, at least at first here, there's an application for precast concrete. What's really promising is the latest research out of Rice University. They studied all sorts of different fly ashes and slags to be able to optimize the use of sort of calcium-rich fly ash and nanosilica and calcium oxides to be able to use less than 5% of the traditional sodium-based activators, meaning that now you can make concrete with a lot less of the activator, which brings the cost way down, plus the ability to handle that caustic material to a point where it may be commercially viable. So this is something to be looked at for the future. It actually has been used. There's an example. I'm sure there are more examples of this. The one that we found was the Global Change Institute in Brisbane, Australia, where it's Australia's first carbon neutral building and one of the first living building challenge projects. It's the first building to include structural geopolymer precast concrete, resulting in significant reduction in the carbon footprint of the concrete for the building, obviously. So there's some promise with this material, but it's probably not something that you can achieve today, in the kinds of volumes that you normally need on a building. Maybe something to be thinking about for perhaps a case opportunity for a small project or maybe a portion of a project. With that, I'd like to transfer the presentation over to Don Thompson to complete the session today.
Thank you, Lionel, and thanks for joining us, everyone. I will pick up now talking about natural and enhanced carbonation, this process of carbon capture. Concrete has the natural ability to absorb carbon dioxide. The carbon dioxide penetrates the surface of hardened concrete and chemically reacts with cement hydration products to form carbonates. So it effectively mineralizes the CO2 and permanently removes it from the environment. It's really kind of a natural process of reversing what's called calcination, which is the process during the manufacturing of the cement in the concrete, where limestone heated to high temperature releases CO2 as it's transformed into the Portland cement product. So this is just a reversal of that process during manufacturing. It's a slow process for in-service concrete. Theoretically, given enough time and idealized conditions, you could see all of the CO2 emitted from calcination absorbed by concrete in the environment, but real world conditions are far from ideal, so that typically does not occur. All right. Let me go here. All right, there we go. The CO2 uptake is greatest when the surface to volume ratio is high. So when concrete has been crushed and exposed to air, that's a way to optimize this process. But even with hardened concrete that's been in place, and a study done and published back in 2015, attempted to look at estimates of how much CO2 was sequestered in concrete placed between the years 1930 and 2013. And the study found that 4.5 gigatons of CO2 was permanently absorbed by the hardened concrete throughout the world, which represented 43% of the CO2 emissions from the production of cement. So basically, we're looking at carbonation of cement products representing a substantial carbon sink and a game-changing development. And our industry continues to look for, or continues to investigate ways to accurately quantify this process, which will then impact the understanding of concrete's role in permanently helping to reduce greenhouse gas impacts. As I mentioned, the best type of concrete for this natural carbonation process is crushed concrete, which can absorb more CO2 over a shorter period because you're maximizing the surface area of the material, so it can be more effective in that absorption. And typically, concrete is not thrown away. Its weight, its volume really moves it more towards continual recycling. And so you see it crushed and oftentimes used as roadbed or as backfill. It can even be used as new aggregate for, or as aggregate for new concrete. Ideally, studies have shown if you can leave the crushed concrete exposed to air for a period of 1 to 2 years before reuse, you're really enhancing and maximizing this process. So there are a number of entrepreneurs that have looked at this natural carbonation process and have been successful in developing ways of enhancing the production of concrete products by taking advantage of this ability of concrete to absorb CO2. One such process developed by a Canadian firm takes purified and liquefied waste carbon dioxide captured from various industrial processes, and it injects this CO2 into the concrete during the mixing operation. And in that process, there's a creation of artificial limestone or mineralization within that ready mix. The developers of this process indicate there's a small amount of CO2 that's sequestered in this process, but probably more importantly, the compressive strength of the ready mix that's being produced with this or enhanced with this process, the compressive strength is improved, which allows you then to reduce the overall cement content in the mix. This is a viable process. It's in the marketplace, and there are over 100 ready mix plants nationwide that are taking advantage of this process. Here's an example of a project that was done using this injection process, a 360,000 square foot office building that used 48,000 cubic yards of carbonated concrete, which sequestered 680 metric tons of CO2, which is equivalent to the amount of CO2 that would be absorbed by 800 acres of US forestry in 1 year. Another example of enhanced carbonation is the use of specially formulated cement. And this cement is manufactured in a process that uses less limestone, and in the process of the calcining process, they're firing the kilns to manufacture the cement at lower temperatures. the developers of this process indicate that that results in 30% less greenhouse gas emitted during the manufacturing of this specially formulated cement. And then that cement is then used to manufacture concrete products right now in the precast industry primarily. So you manufacture your precast components and then move them into curing chambers that have a CO2 rich environment. And with this specially formulated cement, the concrete is able to absorb CO2 based on the developers of the process indicating equal to about 5% of its weight. And overall, they're claiming that the concrete produced with this process, the carbon footprint is reduced by 70%. And this has seen some application in the precast industry, and the developers of the process are looking for ways to introduce it into ready-mix construction as well, or ready-mix production as well. Another process is the use of CO2 to treat fly ash or other supplementary cementitious materials. So there's a vessel that's pressurized with, let's say, fly ash, and you infuse CO2 under pressure, and this combination creates carbonates. And the developers claim that it improves compressive strength for the concrete that is then made with this infused SCM material, improves compressive strength by 32%, which then contributes to reducing the overall cement demand. So you're reducing your carbon footprint in that way. It also increases the durability, improves chloride permeability of the concrete that's created. The developers estimate it eliminates between 50 to 250 kilograms of CO2 per metric ton of product that's produced, and does not have any detrimental impact to air entrainment of the concrete that's created. And then finally, a fourth process uses unpurified industrial CO2 emissions from various industrial processes combined with metal oxides, which is then injected into a proprietary process where you have small rock particles or recycled concrete particles that then absorb this CO2 and become coated with artificial limestone. And the developers of this process claim that 44% of this artificial limestone by mass is permanently eliminated CO2 or mineralized CO2 material. And they claim that carbon negative concrete is achievable, and present this example where if you had 1 yard of concrete that contained 3,000 pounds of aggregate, 44% of that by mass would amount to about 1,300 pounds of mineralized, permanently absorbed CO2 material, which then offsets the roughly 600 pounds of CO2 that was generated during the production of the cement used in that same yard of concrete. So by a factor of 2, you're absorbing far more CO2 than was released during the manufacturing process for the cement in that concrete. So based on this example, carbon negative concrete would be achievable. Not yet in the marketplace. The developers of the process are continuing to scale up the process and looking to set up manufacturing facilities so that these artificial aggregates can start being available to the marketplace. So now let's talk about high performance or other examples of high performance concrete. We'll talk about the high strengths, the greater flexibility and tensile strength and durability, increased life, the ability to reduce traditional steel reinforcement and to improve overall performance. Lionel had talked about the Jubilee Church, and that church uses self-cleaning concrete, which uses titanium dioxide mixed with the concrete, which then allows the surface of the concrete to break down harmful airborne pollutants. It's a reaction that's catalyzed by light. It's a photocatalytic process. So for example, nitrous dioxide, which is an airborne pollutant produced by the burning of fuels in cars and trucks, responsible for acid rain, smog, and other problems, and staining on buildings. When that nitrous dioxide comes in contact with titanium dioxide concrete, the sunlight will convert that nitrous dioxide into harmless nitrate salts, which then can be washed away by rainwater. And that's exactly the process that was used by Richard Meyer, the architect on the Jubilee Church, to maintain the pristine, pure appearance of this design. These three large concrete shells that you see in the photo were designed to represent the Holy Trinity. So their pure, pristine appearance is an absolute aesthetic priority. And so with the self-cleaning photocatalytic concrete, this project built in 2003 is still looking as clean and as white as it did when it was first opened, because of this continual self-maintenance process that's possible with this concrete. We have bendable concrete, which involves the use of very tiny fibers that are dispersed throughout the concrete mix. And in doing so, you create 300 to 500 times more tensile strain capacity than normal concrete. So you have much greater pulling resistance, which allows for flexibility to the concrete that's produced. So it has great application for situations or installations where you have repeated loading, heavy loading, intense loading. So paved surfaces, for example, they're going to see a lot of heavy vehicle traffic. For viaduct dampers that are getting concentrated loads and repetitive loading, as well as for components for earthquake or seismic foundations in tall buildings. It also has self-healing capabilities. It's, the fibers help to keep surface cracks relatively small, and then there's a natural reaction that occurs with any kind of moisture that causes latent concrete or cement products to allow for further mineralization, which serves to repair those cracks and restore the durability of the surface. A similar example is ultra high performance concrete, UHPC. In this case, a manufacturer distributes a premix of powder and the fibers and admixtures, which can then be used to create much stronger and flexible concrete. The fibers can be carbon metallic, they can be stainless, polyvinyl, alcohol, or glass fibers, and it results in a less porous concrete versus conventional concretes, more resistant to chlorides, to acids, to sulfates, and imparts a similar self-healing property that we discussed with the bendable concrete. And here's a case study. This was a project built in Miami, 200,000 square foot exhibit space built on Biscayne Bay, subject to sea, air, and salt. One of the questions that came in early in the presentation was talking about types of concrete for a salty environment. And here's an example of a similar type of coastal application where durability was very important, as well as improved strength, because this site had to resist tropical storms and hurricanes. So this bendable ultra high performance concrete was used to create 100 16-foot long mullions. So these thin, slender mullions were used to reinforce the world's largest impact resistant window. So you still had maximized visibility, but you had a window unit that could meet Florida code requirements for hurricane resistance. And then you have conventional fiber reinforced concrete. This is material that's been around for a long time. fibers not as sophisticated as what we just talked about with bendable or UHPC, but still you can incorporate, and many ready mix producers can supply fibers. They can be steel, glass, or plastic that are combined with the ready mix and improve strength and durability. The plastic fibers are primarily used to combat plastic and drying shrinkage cracking. The steel fibers can be used in structural applications to effectively reduce or eliminate the traditional steel reinforcing bars, which then in turn helps to save time and labor on job sites. Here's a case study where helical steel fibers were used to reduce the amount of traditional horizontal steel in this project. This project used insulating concrete forms, and you see a cutaway illustration at the lower portion of the slide. Insulating concrete forms, it's a stay-in-place concrete forming system. It features typically two face shells of insulating materials, so two layers of foam in this case, and those layers are held apart by those black elements running transversely across the formwork. That holds those face shells the required distance apart to create a cavity for ready mix concrete and reinforcement. And then those web ties, as they're called, also extend almost all the way out to the face of the forming to create flat surfaces that run continually vertically to form furring strips or provide attachment points at regularly spaced intervals, so you can now attach your interior and exterior finishes directly to the formwork. So unlike conventional formwork that gets placed, the reinforcement in concrete is poured and then you strip the formwork away, in this case you're leaving the formwork in place to take advantage of the insulation in the formwork itself, as well as the ability to attach your finishes directly to the formwork and reduce steps in construction. So this was the material used on this project in a panelized application to create at 16 stories the tallest ICF project done to date in the United States. And so here you see a photo that shows one of the panels being craned into place. With the lightweight formwork, they're very lightweight panels, easy to work with. The openings were cut out when these panelized assemblies were created off-site, brought to the site and craned in place. With the use of the helical steel fibers, you eliminate all the horizontal reinforcement. And so now it's very easy to butt the panels together and really speeds up construction. Once the panels are in place, vertical rebar is inserted where it needs to be, and then the fiber reinforced concrete is placed to complete the installation. Then we have graphene concrete. Graphene are single layers of carbon atoms made from graphite. And graphite is very inexpensive, and this process is capable of large-scale manufacturing. Not yet something that's commercially viable, but being looked at very carefully. So you take these graphene layers, and flakes of it is combined with mixing water to create the concrete that you're going to be using. And it creates very strong and very permeable concrete, reducing the cement component in the concrete very well, suitable for large-scale production applications. So we're watching this very carefully as well. And then we have self-consolidating concrete, which is a highly flowable concrete. With the admixtures that are typically used, it stays non-segregating, so you're not seeing a separation of the constituent ingredients, which would reduce the strength dramatically. It can be placed faster than regular concrete with less finishing, no mechanical vibration, and improves the uniformity and provides much smoother surfaces, finished surfaces. So here you have 432 Park Avenue, New York. At the time of its construction, it was the tallest residential tower in the United States. It had an exposed exterior grid of this self-consolidating concrete, very smooth finish. And the aesthetic required not just the exterior to have a high quality look, but that aesthetic was allowed to be exposed on the interior as well. So the project very thin for its height, so it was heavily reinforced, and so the flowability of the mix was important for the high amounts of congested reinforcement on this project as well, and also enabling the material to be pumped to the tall heights of this building while maintaining this nice aesthetic that was desired for the project. So that covers all of the innovations we wanted to share. There's really no one single solution that we see. We see the future being one where many of these different innovations will be used in combinations, whether it's the blended cements, the supplemental cementitious materials, the innovative use of fibers, the geopolymers that Lionel mentioned, as well as the exciting developments with carbon capture, which can enable concrete to sequester and permanently remove from the environment more CO2 than is emitted during manufacturing. So with that, I think we'll move on to questions. So I believe we turn it back over to Stephen.
Yep, we ran a little bit over, so we have a little short time with questions, but Patrick, you said you're going to help out with this. We have 3 questions right now. Are you going to take them?
Why don't you go ahead and ask the questions, and Don, Lyle, or myself will answer them accordingly. Thank you.
First question's from Salvador. We work on the West Coast. I think Donnie actually touched on this. What kind of concrete is best for a salty environment?
Lionel, would you be aware of other examples besides what we shared?
You're on mute, Lionel.
On you.
I knew that would happen. So yeah, I mean, when you look at, we talked a lot about the use of these innovations, especially SCMs, to reduce carbon footprint, but honestly, they've been used for decades to address other performance needs like strength and durability. So in a salty environment, whether you're up north and using salt to de-ice roadways, or on the coast where you might have salt air and moisture that may be infiltrating concrete. The point being is that you really need concrete that's really has low permeability, and the way you accomplish that typically is combining Portland cement along with other SCMs like slag and fly ash to reduce that permeability. So that's the other benefit of using those materials. That's the reason why SCMs are used. The additional benefit is that it reduces carbon footprint.
All right, Steve. Goddard's asks, when limestone is increased in Portland cement mix, is there more effervescence effect?
So I had a chance, because I saw that question, to do a little bit of research, because I wasn't sure of the answer of that on that one. And as it turns out, in fact, it reduces efflorescence. And there's a great example of a project at the University of California, San Diego, where they're building this whole new residential development for the students there, in addition to classrooms and other amenities. And there's a lot of exposed concrete. And the reason why they're using Portland limestone cement, in addition to reducing carbon footprint, is because the color of that cement results in slightly more buff-colored concrete. And apparently on that campus, I've never seen it myself, only images and photographs, but they use a lot of exposed concrete on that campus. And this was a way for them to take advantage of that. And turns out that efflorescence is actually reduced, from what at least my reading, as a result of using Portland limestone cement.
I like John's question that's coming up. Has anyone experimented with using recycled plastics in concrete? It seems like it could be shredded and used in concrete similar to fiberglass.
Interesting idea.
Well,
I'm not aware of anyone doing it. I'd be concerned about the quality or the consistency of the recycled material, that you could count on it in a structural way.
Yeah, I think probably I would see it as, and I've seen presentations and read articles on the use of plastics or rubber And you know, they import different qualities on concrete. So structurally, yeah, they would not be probably very useful, but they may impart other qualities like, the one example I saw was using shredded rubber that imparted this quality of concrete that allowed it to crush, and it was used in crash zones for roadways. So the barriers were made with this rubberized concrete, in a sense, to reduce the energy for you know, car impacts. So likely that there would not be any you know, strength gain benefits or durability benefits of the use of plastic, but amazing the kind of things you can put into concrete and still make it work. It's a very resilient material that way. So you know, glass is another example. Crushed glass is a pozzolan and can be used in concrete. The biggest problem, of course, is volume. You know, can you get, it seems like we use a lot of glass, especially you Californians that like to drink your wine, and we like to drink your wine too, but there's just probably, again, in sort of boutique applications, just like some of the other innovations that are still just in their infancy, we could probably make small amounts of concrete and use it as a pilot project on larger projects. So I think it's worth exploring, like anything else. You know, can we use waste plastics in concrete? I'm sure we can.
It's kind of a local question for Los Angeles. Not sure you can address it, but would any word on when Los Angeles will approve the helical steel pins in concrete?
Helical steel pins, is that what you
Wonder
call
if
it?
he means helical fiber.
Brad, do you want to try to type in the clarification?
So my guess is that we're not going to be able to answer that question, even if it is a fiber question. Right now, we are, just to let you know, we're working on a change in the ACI 318 code that would permit the use of helical fibers. It's permitted now in the code, but it's one of those you know, requirements that as a structural engineer you have to demonstrate that it works and everything else. It's not.
Steel rebar.
Yeah, so I'm not aware of that issue. My guess is that it's something that probably needs to be addressed locally.
Yeah.
Same with steel fibers. Now again, we're working on ways to be able to include it in the code, make it very specific. Hey, you can use fibers, and here's how to design it.
Yeah, being a LA person myself, it's city of Los Angeles can be real tough. So we're down to about 1 minute before. So any other questions that come in will be taken care of and actually answered and posted online. And if you made it this far, we will submit you for the AIA CA credits. It should appear on your transcript within about 2 weeks. A big thank you to Lionel, Dom, and the National Ready Mix Concrete Association.
Steve, can I just share very quickly just a couple of remaining slides just to talk a little bit about the Build with Strength program that we're all a part of?
Yeah, 1 second. Let me just finish one thing. I just want to tell everybody that they can also go on to California's website. That way, if they want to leave, they can go ahead. AIACalifornia.org/climate-action. And all this stuff will be posted on that website later. So, all right, Don, fine.
Great. Thank you, Steve. So Lionel, Patrick, and I are all members or support the Build with Strength program. And one of the things we have is the Design Center, which can provide assistance at no charge for projects that you have in early design stage. So we can look at structural system recommendations to demonstrate how to optimize the use of reinforced concrete, do cost comparisons, both looking at first cost as well as long-term cost of ownership. So particularly looking at comparisons between steel or wood frame examples in concrete. We can review your specifications to cover a lot of the things that you saw in this presentation and help you to optimize your current concrete specs, as well as pull together a local design and construction team to help with collaboration if you're looking at considering reinforced concrete to help answer the questions that you would have. This map shows the Build with Strength Design Center team. We're based all over the country. You can see Patrick's contact information. He covers California and 6 western states, or I guess 6 western states, including California, excuse me. So that's where you'll find Patrick. He's your local Build with Strength rep. You're going to get a copy of this presentation, so you'll have this information for your use if you have projects anywhere in the country. We also have a strong building codes team. So if you have any codes or standards related questions, you can reach out to Lionel or to Patrick or to me, and we can put you in touch with the appropriate member of this team that can help you with issues related to things like fire safety, structural issues, resilience, or sustainability. And finally, if you're looking for more education, you can go to the Build with Strength website, to our education section, and you will find a variety of on-demand presentations where you can look at greater detail about various aspects of working with reinforced concrete for your projects. And with that, I just want to thank AIA California on behalf of Lionel, Patrick, and myself. And we look forward to any questions or working with any of you. I also want to thank the California and Nevada Cement Association for helping support this effort today. So with that, I'll close and say thank you all very much. Everyone stay safe.
All right.
Thank you so much.
Thank you.
Thanks, everyone. Thank you.